All right, so I got a very, so the way, so this is going to be how this lecture is going to work today. So first, a couple of administrative stuff about the final project. We'll discuss exam 2 and exam 3, and then we will do we'll do the 2 Monte Carlo approximation questions that were on that I put on practice exam 2 that I said, hey, this will be good for the next exam. So we'll go ahead and do those. So first, I got a very excellent question about, which is for those of you who are choosing final projects to be video games, this is relevant. And the question was, are you allowed to use other people's assets to for creating your video game if that's your final project? In other words, can you use somebody else's art? And the answer is yes, if you have permission. That means that your best bet is public domain, meaning that it's stuff that is copyright free, or something under the Creative Commons license, or something that is a free asset that's given out by an individual or a company. In the latter 2 cases, in Creative Commons, that's typically by attribution. So make sure you give the artist credit, and same with the other one. If you use somebody else's work, be sure to cite it, for those assets, because, we've all seen my handwriting, right? I'm not exactly a talented artist, so I would totally use somebody else's stuff. But again, be sure to cite those if you're doing a video game with those. Similarly, if you have not submitted your proposal yet, please do so. If you're still, for some reason, having a hard time committing to that or figuring out what that is, please meet with me. Although my suggestion will probably be make a choose your own adventure game with Ren'Py, generally because that's direct and it's easy to be creative with that. Okay. So exam 2. That was 2 weeks ago. We didn't really have a chance to talk about it before, since then, because I hadn't had the chance to grade it, until this past weekend. Yeah, that went pretty badly, but it's not completely your fault. That's a lot of that's on me, as it turns out. I feel like that the first question was definitely a bit too big of had a bit too many moving parts to it to make it relevant, to make it, reasonable, especially in the 15-minute time period we had set up. And then in addition to that, the other questions there. From what I've gathered from speaking with other students and speaking on the Discord, right, the overall consensus is that the questions were appropriate. They seemed to be of the appropriate difficulty and solvable, but you didn't have enough time. And so does that feel correct, everybody? Okay. So if you didn't see the announcement, what's going to happen is that I will drop your lowest exam and group exam, combined score to, we have 3. We have an exam coming up next week. And so that's what I want to talk about. So first thing I want to discuss is how useful are you finding the group exam? Yes, you want to keep that? So I got some yeses there and some no's. Okay, by show of hands, just to see. Yeses and nays. So, okay, so are you okay with being put on the spot? And because I do want to know why. But you can also not.
No, that's okay. I think just like if I had that time to just work on my exam, I would be able to finish that.
That's a valid point. And again, I think the issue with the group exam is that again, this was my first time trying that. So I think that the amount of time that I used for that was a bit, again, misguided. So for exam 3, this is my plan for exam 3. I plan on, at least for the solo exam portion, I plan on doing probably 3 or 4 questions. One question will be, if not an exact duplicate from the solo portion of exam 2, then basically the same thing with the serial number shaved off. Okay, so very close to one of the questions that I'll look at one of the questions. So like if it was the one where you converted the date format to the Japanese date, Like if I did that for a duplicate of that on exam 3, it would be a different date format, right? You know, if it was one to set all the odds to 0, it would probably be something set all the evens to zeros or all the multiples of 10s to 0, something like that. So something very similar to one of the questions you've already gotten. We will also have the second question will most likely be a much more simplified file reading question along the lines of, you know, here's open a file, give me a average of all these numbers, something like that, or sum up all the numbers, something about much more direct and straightforward. And the third question will be Monte Carlo. There will also be, and I think for the group exam, we'll also probably do the same Monte Carlo and some other questions. Yes. If you're happy with your grade, yeah. You have the option to skip exam 3 if you're happy with your grade. Yes. When is the exam again? Next week, next Thursday. Yes. Yep. Yeah, it's 2 exam grades plus the final, right? The final is something different than the exams. Yes.
If we do good in the exam 3, then we skip the final.
No, the only way you can skip the final is having one of the best projects. Okay. So, yes. So so this is how choosing the best project for has worked in the past. I typically ask the TA to choose the best projects, plural, or the best project or best projects from each section. And then I choose from that short list. And if I can't, and then I choose at least one from each section. If I can't decide between a section, or I find there's just one that I cannot exclude, you know, like because I found it personally so good, I'll also include that. So in other words, at least 6 projects will be able to skip, and that's equates somewhere between 6 to 18 students, depending on the group sizes. Okay, so, okay, question from chat. Is there going to be a question on the dictionary on exam 3? Probably not. I want to try to keep it fairly condensed because based on what we've learned for exam 3, if students do fine on exam 3, I might add a dictionary question to the final exam. So, but other than that, I think I'll leave out a dictionary question for the, I'll probably leave out regular expressions from the final exam as well, but I will go over them on Tuesday because I am not going to skip going over on regular express. Well, sorry, if I didn't. Well, you probably want review on Tuesday, so I will probably go over them when we get back because I will not go over regular expressions. Regular expressions are just too useful. All right. So, but again, the main focus will be Monte Carlo because the Monte Carlo problems can be broken up into multiple parts. Okay. And again, I will try to try to consider, okay, let's make sure that this is doable within a more reasonable time within the time limit. All right. So let's see. Monte Carlo, that one. Yeah, we'll start with the Monopoly one. So this one is actually one that I have given out in an exam in previous years. It is in the board game Monopoly, right? So when I introduce a rule, I'm not going to, or a game, I'm not going to assume that everybody has played the game, but I will give you enough to work with what you need. So there's a popular board game, Monopoly. Most of you have played it. Most of you have not played by the rules because nobody actually reads the rules of that game. But in board game Monopoly, you move around the board using a pair of 6-sided dice. So you use 2 6-sided dice. And it's standard thing. You roll, if I rolled a 7, I'm going to move 7 spaces. However, there is a clause in the rules about rolling doubles. In other words, rolling the same symbol on each dice. So if I roll a dice and I get a 3 and a 3 and a 5 and a 5, I get essentially what amounts to an extra turn. I get to roll again and take another action. And then, so if I roll 2 5s, I can roll again. And if I roll a 3, I can move 3 more spaces and either pick up that card or buy that property or whatever. But let's say I roll, okay, it's my beginning of my turn. I roll 2 3s. I move forward 6 spaces. And I now, because I rolled 2 3s, I get to roll again. And I roll 2 1s. I get to take another second turn, another extra turn. Okay. So I can do that. So I can basically do, 3 moves essentially. So, however, if I get 3 doubles in a row, then this does not, just keep going on ad absurdum. Essentially what happens is that you get arrested for speeding and go straight to jail at that point. So you go to the jail space on the Monopoly board where you are stuck until you roll a double. Okay. Sorry? No, it's until you roll a double. Check your rules. It's one of those things like, so what we're going to do is that we want to simulate what are those chances for each of those events, which is rolling it. How often do we just have a turn that goes normally? How often do we get a turn where we get an extra move? How often do we get a turn with 2 extra moves? And how often do we get a turn that we get arrested for speeding and go straight to jail? Okay, so now this can be, as I've mentioned with almost all the Monte Carlo approximation problems we've done, this is something that we can solve with statistics, but that's hard. We don't want to do that. It's sometimes a lot easier to just simply simulate it. So the grading for this is as follows. We're going to simulate 100,000 of these dice rolls. Then I'm going to have an if-else statement for handling these doubles and then handling 2 and 3 doubles in a row. In other words, the term where I get really lucky and the term where I get 3 doubles is the one where I get arrested for speeding. And then presenting the data as percentages. In other words, making sure my data is clean and nice to look at. Okay. And a footnote here that I added was saying that you can roll the same pair as you did the first time. Okay. Right. So you can roll 3 3s and then you can roll 2 3s and then you can roll 2 3s again. So let's boot up Visual Studio Code and get to it. Okay. So let's go ahead and I will save this as on the desktop as Monopoly .py. So we have a Python file now. So for every single program that we do with a Monte Carlo approximation, we are going to need to import random. If you forget to on your exam, that's not going to be a big deal. Other than, sorry, if you forget to drop that in your answer, that's not going to be too much of a big deal. But it will be a bit of a nuisance when you try to do randomization. When you're trying to test your code. Okay, so we've got a random library. So first thing we want to do is simulate rolling a die. Now, here's the thing. Despite this being a game of a Monopoly, which means that we roll 2 6-sided die, we roll a pair. I don't want to roll. I want a function that is only going to roll 1 die at a time because I need to make sure if they match. I need to check if my 2 results match. Not only that, we want to make sure we get the right statistical distribution. There's a difference between rolling generating a random number uniformly between 2 and 12 and rolling 2 6-sided die and getting a bell curve. So we'll just write our standard roll that we've done for other programs, which is we define roll and we'll just simply return random.randint 1 through 6. Now, there are other ways to do this, of course, right? There's plenty of other ways to do this. The other way that I find to be useful when we're dealing with random numbers like this, especially if we're dealing with weird dice, like if you've ever played Mario, some of the Mario Party where they have dice that are stacked a bit weird, where they have like an uneven distribution of numbers, right? If you have some kind of die that has and you want to manually specify what's on the face of the die, you can create a list, 1, 2, 3, 4, 5, 6 in this case. And then rather than choosing a random number, we can do random dot choice and select one of those at random. Those are both the same way of doing things. Do I care how you do it? No. But it's good to remember that random dot choice is one of the more useful functions that exists. It's something that Python has, and I wish other languages really, kind of made it easy to as easy to use. All right, so we've got our function for rolling a die. Now we need to simulate essentially. We need to do a single thing of what we're simulating. In this case, the case of turn. Okay. So here we're counting the number of, so here what we're going to do, what we care about is the number of doubles that we're getting. So normally in previous questions of this type, we've been returning true or false, right? True if I won a game or false if I lost a game. Here though, we want some kind of outcome, and there's 4 different outcomes, right? There's no doubles, 1 double, 2 double, 3 doubles. So in this case, I think we should return an integer, which is how many things, which is how many of those extra turns we got. So we'll go ahead and do that. And we're going to do our, so I'll call this. So now let's go ahead and roll our dice. D1 is equal to roll, and D2 is equal to roll. So we roll 2 separate dice. One of them, and I keep emphasizing this because one of the most common mistakes I saw when I had given this out as a question before I changed it into a practice exam question is that some students in a rush probably did this, which was that they would roll the die and then multiply it by 2 to try to roll it twice. But all that does is multiply your result by 2, which means that now your only legal rolls are 2, 4, 6, 8, 10, or 12. So just doing it, atomically like this, one piece at a time is very useful. So we have 2 dice and we roll them. And we can now start a very straightforward kind of if-else statement, which is that if D1 and D2 match, then we've rolled a double. Now I'm going to put pass here because I'm going to come back to that. If they match, great. We're going to have to do this all over again. Else, well, we didn't get a double this time. And so we can end our simulation of the turn right now by saying, hey, we didn't roll a double, so we'll return 0. Okay. So now if I rolled 1 double, I got to roll again and see if I get 2, which is fairly straightforward. I'm going to be lazy and I'm going to copy paste this and roll them both again. I'm not going to try to do anything fancy like recursion because that would just be a mess trying to remember how often, how deep this went. D1, roll, D2, we roll again. And we're going to ask ourselves, do these match? If D1 equals D2. And I'll pass again, because if they don't match, well, then this says I rolled 2 pairs. So I rolled I rolled 2 values that were the same. But when I rolled again, I didn't get things were the same, so I rolled 1 double. Otherwise, I rolled 2 doubles. And so we repeat this again. So if I rolled 1 and they're the same, and then I rolled 2 and they're the same. Okay. Then I'll roll it a 3rd time. And I have to ask myself, this is the last one, I swear, which is I ask if they match again. Okay. Now, if I've rolled them, if I rolled a pair and then I rolled another pair and they matched, and I rolled another pair they matched, that, right? If all 3 of those if-else statements are true, then then I've gotten arrested for speeding. I've rolled the maximum number of times. So the maximum number of doubles. So return 3. Otherwise, return 2. So now the other way you can do this is you can look at this and go, the maximum number of, I'm going to roll 3 pairs total, right? And if the first one matches, basically I'll just simply ask, okay, if I've got one match, if I've got 1 and 2, and then if I've got 1, 2, and 3, which is a bit of a different logic that you can use. There are multiple ways to do this, but this is the most straightforward. So let's go over that again, right? So I roll, if my dice don't match, return 0. If they do match, check again by rolling. And it's important that you roll new numbers. If you reuse the same numbers, right, you're going to get into a bit of trouble. So if I roll my second pair, then I'll move and try to roll my third pair. If I don't roll a second pair though, I'll return 1 because I only rolled 1 pair. If I rolled my 2 pairs, but don't roll a third pair, return 2. But if I do roll 3 pairs in a row, return 3. So I've created a simulation of this turn. And so we can test this now by simply printing it, print turn, call it, run it. And there we got 0. So no match there. 0. Really going slow there. 0. Now, getting a lot of zeros is a fairly, common outcome, because what are the chances that 2 dice come up the same? It's 1 in 6, right? So, and here I got 2 of them to match, which is actually fairly low odds, 1 in 36. So now let's go ahead and do this simulation. So we want to do 100,000 of these dice roll. So trials is equal to 100,000. And we just simply do this. We create a for loop to run this 100,000 times. Well, I've already created a variable for it, trials. And we would simply generate, and we'd simply simulate the turn, but we need to collect our outcomes. So there's a couple different ways we can do this. There's only 4 outcomes, so we can do it either with dictionaries or without dictionaries, right? With dictionaries, it would look something like this, right? We would have outcomes is equal to, and then we can either leave it blank and then add them in as we get our results, or we could pre-program in, we've got 0 zeros, 0 ones, 0 twos, right? And 0 threes. Or we could just simply create, since we know there's 4 different outcomes, we could do nones is equal to 0, single equal to 0, doubles is equal to 0, and triples is equal to 0. How many times did we get a pair? Once, 0 pairs, 1 pairs, 2 pairs, 3 pairs, right? And then write an if else statement based on the outcome, right? So we would say something like this: result is, we get how many pairs there were, and then if result equals 0, nones plus equals 1, if result equals 1, singles plus equals 1, you get the idea, right? If we do dictionaries, on the other hand, If we do dictionaries, on the other hand, we can make this a lot more condensed. All right. And that's why I like using dictionaries. Outcomes is equal to this. And I'll go ahead and pre-populate that because it's easier. So, right, the keys are the results and the values are how many times I've seen that result. So I've seen 0, 0 times, 1, 0 times, 2, 0 times, and 3, 0 times. Yes. Pre-populating it, I could just simply add it on the fly, and then I would simply have to make, but doing it this way ensures that everything's sorted. Yeah, I could totally do that way. Okay, so, and in this case, we would just simply do outcomes result plus equals 1. Just simply for that result, increment the number of times I saw that outcome once. And that negates the need for the if-else statement you were talking about, the if-else statement where you say, if you've seen this once, if I've seen this before, increment it, otherwise I've seen it once now and it's a new key. Now the last part is we want to figure out how often we saw each of these. So if we were just using the variables, we would just simply print out nones divided by the trials, singles divided by the trials, doubles divided by the trials, and triples divided by the trials to figure out the percentage. Here for this one, same idea, num doubles in outcomes. So for print and how many doubles there were, and then outcomes of that divide by trials. So we simulate this and we see that, and again, doing 100,000 of these simulations isn't very hard for our computers, right? Here we have an 83% chance of not rolling a pair, which makes sense. That's about 1/6. Then a 13% chance of rolling a pair, and a 2% chance of rolling 2 pairs in a row, and then 0.5% chance of just going directly to jail. And if you want to get more accurate, you increase the number of trials that you do, because that will add the number of significant figures you get in your outcome. But at some point, as we see over here with 83, your significant figures, start mattering less and less. 83% is what you wanted to know in this case. Any questions on this one? All right, so next one is a bit of a trickier one, but I'm a fan of this. It's based off a game, and now, as you know, and as you've come to learn, I really enjoy, trick questions, or rather questions that have tricks in them, I should say, not, tricking you, but rather like these kind of things where the statistics look like they should be even, right? You should have even odds of winning something, but of course the rules are stipulated in such a way that that you're going to lose the game, right? So this is a game called Penny's Game that I'm describing here. So, and I'll talk to you about where the trick is here. So the outcome of any fair coin toss, right? In other words, we're using a non-weighted coin. It has an equal probability of heads or tails, right? If I were to toss a coin 3 times in a row, right? There's 8 equally probable outcomes, right? These outcomes are all equally likely. Throwing 3 heads in a row, 2 heads and a tail, a head, a tail, and then a head, and then followed by two tails, right? Or I start with a tail, have two heads, tail, head, tail, 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 head, tail to tail. These are the 8 outcomes I can have, right? Where order matters, okay? Right, my first coin flip, my second coin flip, my third coin flip. These 8 outcomes are equally likely. That's not the trick here. I'm not trying to trick you here. These 8 are actually all equally likely to occur. Those are the 8 different outcomes you can have for rolling 3 coins, for flipping 3 coins, right? 2 possibilities times 2 possibilities times 2 possibilities for a total of 8. Okay. So suppose I challenge you to a coin flipping game called Penny's Game for $100. Okay. You choose a sequence that one of these 8 sequences. You're going to choose one of these 8 sequences. Okay. And then I will choose one of those 8 sequences. And then we will flip a coin. If your sequence comes up first, you win $100. If my sequence comes up first, I win the $100. Right? So here's some example flips. Right? So suppose that you choose head, head, tail, and I choose tail, head, head. Right? So if head, head, tail comes up first, you win. If tail, head, head comes up first, I win. So, right? So suppose this is the sequence of flips: heads, tail, head, tail, head, tail, tail, head, head. It ended with the last 3 were my sequence. So I win. Head, head, tail, you win outright. Tail, tail, head, head. Right? I won. And then we keep flipping, and then in this one, we keep flipping a coin and it keeps coming up heads, but as soon as it comes up as tail, you win, because the last 3 would be head, head, tails. Right? It seems like a fair bet. After all, we already discussed that these 8 outcomes are all equally likely. So it's just as equally likely that yours will come up first as mine will come up first. That's the lie. That is the lie. I am lying through my teeth right now. That is not what's going to happen. Right? Because what was the rule? The rule was you choose a sequence, then I choose a sequence. Not one of us chooses a sequence first and the other chooses one. You choose a sequence, then I choose a sequence. That gives me control. It doesn't seem like much, but it is everything. It is enough to reduce your odds of winning to 1/8, depending on what you chose. Okay? I'm not going to, remember, I am not going to challenge people to games of chance for the stakes of $100 unless I'm pretty darn sure I'm going to win. Okay? So this is a game called Penny's Game, and the trick here is, I believe that let's see, yes, you did tail, I did, let's see, I forget what it is, but basically based on your choices, I move one of the choices to the back and flip my other coin choices. But if I do that, what happens is that my choice subsumes your choice. The only way you can win is by throwing 2 heads followed by a tail. So in other words, the only way you can win, if you think about it, if your choice is head, head, tail, is that you throw head, head as your very first thing. As soon as you throw head, tail, head, as soon as you throw one head followed by 1 tail, well, that begins my sequence, which is tail, head, head. Yes. Sorry? If they get, yep, they have to get 2. It's the only way you can win, if you get 2 heads in a row. But as for me, I basically, as long as, I win with a fluctuating sequence. Some of these are much more dominated than others. So, but let's see what the odds are. Okay, again, this is like the Monty Hall problem. It doesn't seem like much on the outset. But again, trying to prove it with statistics, that's hard. Instead, let's prove it by simulating it. We are going to simulate two we're going to have player one sequences and player one and player two sequence. Have your game simulate that game, create the game, simulate it 100,000 times, and then calculate the percentage those two players win. So let's go ahead and I will go ahead and just use the same file. I'm going to go ahead and comment this out by going over here, dropping and turning this into one giant string that will get read and then completely ignored. Okay, so now again, import random to begin with. So here we're going to do a coin flip. Now there's a bunch of different ways we can do a coin flip. Like there's a lot of different ways. So for instance, def flip. We could represent our coin flips with numbers like this. We could represent them as random.randint, a 0 or a 1 for head or tail, or we could do a 1 or a 2, right, for head or tail. But that's a bit hard to remember because that's just one more thing I have to remember, which is translating 1 to 1. In this case, again, readability is everything, right? So here, I'll just create a sides variable, even though, right? I'll create a sides variable and I'll create a list that has a head and a tail in it, right? 2 items in it. And I'll use the random.choice that I talked about earlier and choose one of the sides, head or tail. And it's going to be 50-50, right? Python says that it will choose, let's see, chooses a random element from a non-empty sequence. When it talks about random, unless it specifies it's uniformly at random, meaning that nothing has more weight than anything else. Okay, so that's our flip function. So def game, and here I'm going to provide two arguments, which is I'm going to provide sequence 1 and sequence 2. seq, short for sequence in this case, for player 1 sequence, and players 2 for players 2 sequence. This way, I'm not going to be hard coding, the 3-letter combination that we'll be using. Here that way we can test it on the one that we've been given, but also test it on other ones to see what the outcomes would be, okay? So in this case, what we've got is that we will, I'm going to create a variable called, we have this flip function. We could call it flips here, but let's call it outcomes. So we don't, have some 2 variables that are named the same, very similar thing. Or we can call it, yep. So, and this will just be a list. And what we'll do is that as we flip a coin, we will add it to this list. Or actually, rather than a list, because we're dealing with strings, we can just make it a string, right? And as we keep doing this, we can just keep concatenating to the string, keep adding it. And then we will just simply check the last 3 letters of that string. And if it matches player 1 wins. If it matches players 2, player 2 wins. All right. And this is one of those few cases where it's okay to use this thing where I tell you not to use it, which is while true. Because honestly, it's going to go on, and because when you run a while true, there's only 2 ways to get out of it. You break out of it or you return, which stops the function. Here, as soon as we detect as soon as we detect what's going on, we will return. So in this case, it's quote unquote safe. Again, the other way to do it if we really want to avoid using a while true, we can say done is equal to false, and then do while not done, and then return afterwards. But I'm on a test. I've got, this is an exam. I want to code as fast as possible. So while true, flip. So I'll flip it. That's going to generate a string. Outcomes is equal to outcomes plus this. And remember, adding two strings together is just basic string concatenation. It glues the strings together. So, and all I'm doing here is I'm just getting the result directly rather than storing it in a variable. Right? I could store that in a variable and then add it, but I'm not. The other thing I could do is I could just reduce this to plus equals, but again, I just want to emphasize that that is what plus equals means. Okay. And now we just have two if statements. If the last three letters of the outcomes is equal to sequence 1, then the player won 1. So -3 to the end. Okay. Else. So if outcomes -3 to the end. So this is the last three, this amount. So remember, negative indexes, -1 is the last one, -2 is second to last, -3 is third to last. So from 3 to the end. So that means the last three letters, if that's equal to sequence 1, return, well, we'll need to return something. I'll return 1 to indicate that player won 1. We could also do true or false, but otherwise we will do an if statement over here. If outcomes, it's the same thing over here. If outcomes is equal to sequence 2 in this case, right? If the last three digits are match player 2 wins. That's all a game is. This game was very short for us to program, even though the logic of it was a bit weird, right? And again, the slice notation is really nice in Python. It makes a lot of this job easier. Okay. So let's go ahead and simulate a game. Print, and we need and we want to do our two things were head, head, tail, and tail, head, head. Okay, so we'll simulate this with head, head, tail, and tail, head, head. Okay. We run this, and player 2 wins in this case. Player 2 wins. Player 2 wins. Player 2 wins. Player 1 won. Player 2 won. Player 2 won. So yes. So the return break ends a function, which will, by virtue of ending the function, it ends the while loop. Again, if we don't want to do this, we could just simply say, we could do it like this. Winner is equal to 0, and do something like this. While winner is equal to, this is probably the safer way to do it, which is while winner is equal to 0. And then say winner is equal to 1, winner is equal to 2 over here. And once winner is equal to, is set to 1 or 2 in this case, then our loop ends and we can just return the winner. It's effectively the same thing. I've just added 2 more lines, but I've removed the while true loop, which is, always a nice thing. Yes. Uh-huh. Yep. Right, because it's one, because we're one of us is flipping a coin. There's only one coin being flipped, and we're asking what the, and we're basically, whichever sequence comes up, whether it's mine or yours, that's the player who's win. It's not who's flipping the coin, it's which sequence. Okay, so, and I mean, like, again, if this is a scam, I'm gonna give you the coin to flip, so it's your darn fault that you're losing. Okay. So, but as we can see here, that I keep getting 2. I did get a 1, so it's not like this isn't wrong, but yeah, see, I got a 1, so this is working. It's just that, as I mentioned, this really does seem to be a game that is rigged in my favor. So let's go ahead and do our simulation. Trials is equal to, we'll do 100,000 games. And I do 100,000 because, again, that is something that is a lot, but it's not trivial, but it's trivial for the computer to do. Okay, so trials is equal to this. Okay, so now for underscore in range. Let's see, trials. Sometimes I lose my train of thought there. Okay, turn. Nope, sorry, game. This is because this is doing a game. Then this game is going to return some kind of outcome. So player. So here I can do just player 1 wins. So when I've got like 2 outcomes, I only need to count 1 outcome if there's 2 outcomes, because the other outcome is just simply, the complement. I can just simply, the number of times I want is that player 2 won would be the number of times player 1 lost, assuming there's no ties in this game, right? So let's go with wins. So this is the number of times player 1 will win, okay? So the number of times the Rube or player 1 or the Mark will win. So game, we pass in 2 right? We pass in our head, head, tail, and tail, head, head. Double check. Head, head, tail, tail, head, head. Outcome is equal to this. Or let's go ahead. Actually, we can call it winner, just like we did in the function. If winner is equal to 1, wins plus equals 1. There we go. And then we can very easily calculate the win rate by saying, hey, wins divided by trials. Okay. And then I can calculate the other player winning by saying the number of trials minus the number of wins divided by the number of trials. Right? And so these 2 numbers together add up to 1. Okay. So let's run it. And we see that player 1 has a 25% chance of winning, and player 2 has a 75% chance of winning, approximately, right? 74 and a lot of change on there, right? There, it's 25.05% chance of winning, 74.95 chance of winning. So as I mentioned, this game is called Penny's game. Okay. So, and it's, so depending on the player's choice, you can optimize your odds very significantly. So for instance, if the person chooses heads, and you choose tail, head in response, then your odds of winning are 7 to 1. Now, why is this? Because the person who's playing now has to win out. Player 1 now has to win outright. They have to throw 3 heads in a row. If they don't throw 3 heads in a row, there's no way for them to win. As soon as the 1 tail is thrown, that's the start of tail, head. Because what has happened is that this sequence contains the beginning of their sequence. The way you do that, see here, for instance, head, tail, head contains the beginning of their sequence. The way you do this the way that the second player's game is chosen, or second player's choice, is that first choice, second choice, third choice. You take the inverse of their second choice and then their first two choices. So if you choose head, tail, tail, I'm going to choose head, head, tail. And we can see how lopsided this game can become by doing this. Again, 1 in 8, like I mentioned, you can completely skew your opponent's chance of winning by getting it down to 1 in 8. So, any questions on that one? All right. So let me go ahead and I will send out this document tonight with more problems. But I believe I had this one. This one had a lot of regular expressions questions on it. Because my third exam usually had regular expressions, but because of, I've devoted a couple more lectures than I normally do to exams. Because I used to be able to do the exams and labs. Okay, classroom, ITP. Oh, no, okay, I don't have it here. Interesting. Okay, so now, just again, I use GitHub. If you haven't figured it out, I use GitHub for pretty much everything. So here, for instance, I keep all of my, private teaching docs on a private GitHub repo because that makes it easy for me to track changes between stuff. So there. And again, mentioned I reformatted this computer, but all I have to do is push a button and pretty much all my code's there, as well as these practice exams. So, always. Okay, so I'm just looking here for another Monte Carlo approximation problem. Okay. Okay, apparently I didn't include one there. All right. In that case, let's go ahead and I believe I have one on Runestone for when I was doing quizzes on Runestone a while ago. So let's go ahead and pull that up. Because doing these took a lot less time than I thought it would. You had less questions, I guess. But any questions more about Monte Carlo problems? Okay, instructors page. Assignments. Yeah. Pretty much. We're just, yeah, we are essentially just using the for loops and the random module to do statistics. All right. Oh, I remember this one. Okay. I'm going to grab this one. This one was more difficult than I thought it was, but it was a lot of fun. Okay, so this comes from the same place that so remember one of the Monte Carlo approximations I gave was was a game of chance where basically we had, 5 red cards, 2 black cards, right? So this comes from the same book, which is How to Cheat at Everything. All right. So, and Alt-C, there we go. So suppose we're going to do another betting game. This time, rather than dealing with a coin game, we're going to play a card game. In other words, using a standard 52 deck of 52 cards. We're going to take a deck of cards and shuffle it and then cut it into 3 piles at random. Okay? So in other words, we take a deck of cards, right? Your standard 52 cards, we shuffle it and we split it up in 3 decks into 3 smaller decks at random. I bet you that a royal cards are the jacks, the kings, and the queens, will be on the top of at least one of those piles. If any one of those is a royal card, I win. But if there's no royals show up, if all the royals are scared, then you win. Okay. I'm gonna point out there's only 12 royal cards in the standard 52 card deck, right? There's a jack, a queen, and a king of each of the 4 suits, right? So that's 12 winning cards. There's 40 losing cards. Obviously, much more in your favor. So what are the real odds of the game? You know, what are the odds that you're going to win this game? Which is, again, we've got 3 piles of cards. We're going to flip them, and we're going to flip them over. Now, taking the shuffle. All right. So, yep, we've got a list. So 3 points, shuffling the deck. 7 points, taking a shuffled deck and splitting it into 3 piles. The piles can be any size, but each must have at least 1 card. That was kind of a hint that we can actually, that remember, only the top card matters. So just like a lot of things in statistics, we can simplify it by saying we're just going to draw 3 cards, right? But we could also just physically split, we could physically split it into 3 piles. Okay, 5 points is if we select the top card from each of the 3 piles, 5 points determining who won, 5 points for simulating this 100,000 times, 5 points for calculating the real odds. Now, again, when I give you a breakdown of rubrics in points like this, especially in Monte Carlo approximations, this is kind of a direction, this is the directions you should follow to solve the problem. And if you can't solve it, move on to the next one and assume you got the last one right. Okay? So, right? So, how do we do this? So let's go ahead, and this one also came with some code because creating a shuffled deck of cards is a bit of a pain. Okay. So here, an incomplete, yep. So, yep, the ace counts as our 1. It's not in our consideration here. It's not a royal though. Okay. So we have a 2, 3, 4, 5, 6, 7, 8, 9, 10, a jack, a king, a queen, and ace. And then, as was pointed out, I've got a ×4 over here. Remember, ×4 when we do multiplication with a list or a right, when we do multiplication with a list or a string. Here, I'll just simply show you on the console. It makes it, it replicates it that many times. So if I did ha and did multiply that by 5, I'd get ha, 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 ha. So, so the suits don't matter here, right? If the suits mattered, I would not have asked the question because that suddenly becomes a lot of startup time and just making your deck. Here, we have our non-royal cards and our royal cards. If we wanted to simplify it, we could simplify it. I mean, we could also simplify it this way by saying deck is equal to, royal times 12 plus non-royal times 40, because again, we don't actually care about the actual values, right? Both of those approaches would be fine, but when we say create a deck of cards, it's generally easier to actually think about it when we're dealing with real cards. So here, how do we shuffle? Well, we're going to import random, and random has a whole lot of functions built into it, including random.shuffle. All it takes to shuffle something. So this shuffles all 52 cards for us, puts them in a random order. And then all we have to do is we are going to return the deck. This is just simply going to give us our function. Okay. Now we can take the shuffle deck and split it into 3 cards. So let's go ahead and just simply put that in a game function. Def game is equal to bump. Deck is equal to create shuffle deck. Okay. And so now we want to split this up into 3 decks, which we'll do by, there's a couple ways to do it. Honestly, I think what we're going to do is that I'll just slice it at random. So what I'll do is I will choose a index, a target index from, so this is actually probably the hardest part, I would say, which is splitting it up into 3 decks. Yep. There's a bunch of ways to do this. We can, there's a ton of ways to do this. We can, and both of the easiest ways I feel involve generating. So I'm going to go with I'm going to start by showing you the most direct way that involves the least amount of trickery, or kind of just most direct, I think is the best way to put it. So I'm going to create 3. We want to separate this into 3 piles, right? So I'm going to create pile 1, pile 2, and pile 3, right? So the most direct way to actually split this up into piles is I'm going to choose a random number, random.randint, between 0 and 51, right? Those are our random indexes. Actually, in this case, we need to choose it between 0 and 50 because we need to have at least 2 cards left over, right? Right? So between 1 and 50 because we need to have at least 2 cards left over. Num to put in, num to put in is equal to 1 to 50. And then what we do is for in range num to put in. So we do this many times. Pile 1 dot append and then we will do deck dot remove, removes the first occurrence of this value. In Python, sorry, pop. There we go. That's how you do it in Python. Deck.pop. What that does is that removes it removes a value from the end of the list and it puts it in pile 1. And it does it a random number of times between 1 and 50. Okay. So we're going to have some number left. All right. And we'll do that for pile 2. But we're going to have somewhere between 2 and 51 left. So here, rather though, we don't know the hard number that's going to be. We can do subtraction, but why bother doing subtraction when we can, because that's math. We can just simply ask for it, which is the length of the deck. The length of the deck. That gives us now that gives us an index out of bounds. So this gives us how many are in there. So we want to do -1 there because we want to have at least 1 left over, because each of those needs to have 1 in each pile needs to have at least 1 card. So I'm subtracting 1 to make sure there is 1 left over. And so now I just do the same thing for pile 2. This is the most direct, but it's also, required you to know about pop, and it's kind of annoying. And then we can just simply say pile 3 is equal to, is equal to what's left over. Right? And then all we have to do in this case is we would just simply check the tops of the, index 0 for each of those. Right? We'd check what index 0 is to see what was that top. Yes. It removes so it removes index -1 from the deck, and append adds it to essentially index -1 of the other one. So it moves. So essentially what this is doing is that's taking the end of this one and moving it to the end of this one. So we could have done this with slicing, but this way is direct, which is just simply moving. When I see cards and talk about card manipulation and try to simulate that, I always think about it in terms of just moving physically those cards around. That being said, this is a lot, and honestly, only the top card mattered, right? I'm going to check, because what's my next check? If pile 1, index 0, so let's go ahead and actually say, let's go ahead and create royals is equal to Jack, King, Queen, King. If pile 1, index 0 in royals, or pile 2, index 0 in royals, right? That's the first thing. So I could also just choose, 2 random numbers, or I could just simply choose the first 3 cards, from my initial deck, because essentially when I'm splitting it into 3 piles, I'm choosing 3 cards at random to flip over. The splitting up into piles, that's just sleight of hand, essentially, statistical sleight of hand. But so another way to do this, so I will finish up this way, the pile 2's in royals, or pile 3 in royals. So if there was a royal card, I won, so return false, else return true. Oops. Again, when you talk and type, else return true. Okay, so here we have our game. I'm going to go ahead and simulate this, but then I'm going to go back and rewrite it and see that we're going to simplify it and get the same statistics. Because when it comes to card games and stuff like this, where we're drawing stuff at random, right? A lot of times, pick randomly 3 things from it. We can just simply take the first 3 things from the deck, and we'd end up getting the same results. So here's our game. Trials is equal to 100,000 of these trials. 4 in range trials. Okay. Let's see. We want to play a game of this, and if we won this game, so if the game is equal to true, or we can just simply say if game, return, and not return, we would do wins is equal to 0, wins plus equals 1. And then we can print wins divided by trials. And your chances of winning are around 44%. It's not a 50-50 shot. It's about a 44% shot, according to this. Now, let's go ahead. Now, I'm going to, instead of doing all this, I'm just simply going to, instead of doing what we did here, actually, yeah, I will, instead of doing this and splitting up into 3 piles, I'm just going to grab this bit over here. So we still have our created deck, we still have our royals, but that's about it. And this should be statistically the same answer, which, as I say, deck, if the first card in the deck, the second card in the deck, and the third card in the deck, statistically the same thing. Still comes out to 44%. So not a game that you could, that if you're cheating at, you'll win consistently, but it's enough. It's enough to make a difference. Again, these kind of small rates of wins add up over time. Right? And again, the reason why I do so many of these scam / kind of gambling questions, okay, which and you can basically, okay, the reason I do all these scam / gambling questions on these, okay, is because that's kind of where statistics got its start. You know, mathematicians needed a bit of, needed a way to pay some debts off, so some gamblers or royals with or nobles with gambling as a hobby, you know, hired them to ask, okay, how actually does this work? And that's that's kind of got to the start of it. If you're interested more about that kind of history of randomness, I think The Drunkard's Walk, it's a novel, goes, which is subtitle How Randomness Rules Our Lives, goes into that in greater detail. So the thing is that we don't, you're right, but then that gets into a whole nasty philosophical discussion of, if I take a coin and I know exactly the amount of force I'm going to apply to my hand, the amount of air pressure in this room, the temperature of this room, all the other variables that we care about, such as the way the air is moving, can I calculate the way that this coin is going to end up? And if so, is that random still? That gets into a whole nasty discussion. So when we talk about randomness in the context of Python and programming language, we're talking about pseudo-random numbers, which means that they are using a process which can technically be predicted if you know the beginning ways that this starts, but it's statistically random. The outputs create a distribution of numbers at random that follow some distribution. Yes. Yep. I think I've heard that. I know in most US casinos, it would be blackjack, because baccarat, again, I don't know how to pronounce it, but I know what you're talking about. I don't know if that's available at most casinos, whereas blackjack is, universal, and that is the game that has the highest yield, especially if you can count cards. I mean, yeah, especially depending on how, so there's different ways to mess with the statistics of it, but again, in general, the general rules of blackjack, you can, if you play perfectly, that minimizes the house's chance, and then combined with card counting, that can actually change the outcome, the average outcome in favor of the player. That being said, it's not significant enough to win all the time, which means that you can hit a losing streak just like crazy, and it gets into the whole thing. So let me just say this about our final, about the question that we will do on the Monte Carlo. So I've decided on the question I will do for exam 3 for Monte Carlo approximations. And I will tell you that it is one of these kind of games where I'm going to say, okay, you have an even chance of winning this, and I want you to compute the real odds. And it's one of those where you win or you don't. There's not multiple outcomes. It's either a true or false. Okay. And I'll give you one, I'll even go one further and tell you it's going to be a coin flipping game. All right. You don't want to try to overcomplicate it like that. You want to make atomic operations when you're messing with random numbers and moving files. Nope.
Nope.
But again, you mentioned you use Reaper.
Yeah.
So I do think that, like, you know, if you use it and you're a big fan of it, I think this is a perfect opportunity for you to try to write something in RiaScript too.
Okay.
If that's comfortable with you, if you're comfortable with it.
Yeah, I started working on learning a little bit of C++, but it's like the only thing I'm having trouble with is it like it's kind of insistent on using Visual Studio, not Visual Studio Code, and I don't know. It's
what does it want you to do? Visual.
So basically, there's packages for different IDEs. The Visual Studio one, there's the Mac one. So do you know if like I could do it in like Visual Studio Code or something?
I don't actually.
Because doesn't Visual Studio cost money?
If you're a student, no, you should be able to get it for free.
All right, cool.
Okay, so Discord, let's see there, class. Okay, I cannot minimize the Zoom.